Hello. All right, so we're going to do problem 11 from chapter 18. This is the problem from Wiley book. So the problem says, what is the volume of a lead board at 30 degrees Celsius if the board's volume at 60 degrees is 50 centimeters cubed? So let's say we call this initial volume is 50 when the temperature is at 60 degrees Celsius. And now you'll also find V prime when the temperature is at 30 degrees Celsius. So in order to do this, the equation that we want to use is this equation, that delta V is equal to V beta delta T. This equation describes the change in temperature will have an effect on the size of the object because it's going to change the volume. And in order to do that, we identify that V is 50 centimeters cubed, and beta is the coefficient of volume expansion, and delta T is the change in temperature. So we need to figure out what is beta. And beta, we know that is 3 alpha. So ultimately, we need to know what is alpha. So to find out alpha, what you need to do is check out the book from the OpenStack, University College, Volume 2, Table 1.2. That will give you the coefficient of the expansion. So once you check out the book, you'll find that alpha is actually 29 times 10 to the negative 6. So multiply that by 3, you get beta. So beta, you will have 87 times 10 to the negative 6 per degree Celsius. Okay? So once you have that, then we are ready to plug into this equation to find out what our delta V is. Because our delta V is equal to V, which is 50, beta, which is 87 times 10 to the negative 6, and then times the temperature change. The temperature change will be the final temperature, which is 30, minus initial temperature, which is 60. So your delta V, you will get a negative value because you have the temperature decreases, so volume contracts. So you'll get negative 0.1305 centimeter cube. So what is the final volume when temperature is at 30 degrees? It will be V plus delta V. So when you have the 50 and then plus the negative 0.1305, you'll find that the V prime is equal to 49.8695 centimeter cube. So that is your final answer. Okay? All right. So the next problem that I want to do is problem 12. And let me erase this first. All right, let's see what problem 12 is about. All right, problem 12. Let's see. Aluminum alloy rod has a length of 10 centimeters at 20 degrees Celsius. And it has the length changed to 10.015 centimeters when it is at boiling point of water, which is at 100 degrees Celsius. So you're asked to find what is the length of the rod at the freezing point of water. So in other words, you want to find let's call that let's see, L100. So now you want to find the what is L when it's at 0 degrees Celsius. Okay, when the temperature is at 0 degrees Celsius. And then you also find what is the temperature of the length of the rod when it becomes 10.009. So what is that T when this becomes 10.009? All right. So this is a material that is made of aluminum and alloy. So when you check up the book that provides the coefficient of linear expansion of volume expansion, you'll find that you could not find the coefficient for this kind of material. So in that case, you have to find the alpha based on the information you're given. So how do we go about doing that? We know that there's a temperature change, and when there's a temperature change, there's a linear expansion. So the equation that you want to use is based on this. The change in volume, the change in length. So delta L is equal to the initial okay, which is 10 centimeters, and then times alpha because it's linear expansion, and then times delta t, okay? And as I mentioned, because you cannot find alpha from this from the table, you have to actually calculate that based on the information you're given. So you are given 10 centimeters L and at 20 degrees, and at 100 degrees Celsius, the length changed to 0.015, meaning that your delta L, based on this, your delta L is 10.015, okay, minus 10, that is your delta L, and that has to be equal to initial, which is 10, and then times alpha, which we don't know, and then times the temperature difference. So the final temperature is 100, and the initial temperature is 20. So based on this, you can see that on the left-hand side, you get 0.015, and that's equal to 10 alpha, and then times 80. So from this, you can calculate your alpha. So we got an alpha that has a value of 1.875 times 10 to the negative 5th per degree Celsius. So this is the coefficient of linear expansion for aluminum, alloy, that kind of material. And then once we have that, then let's see, what do we want to find? We want to find what is the length when the temperature drops down to 0 degrees. So again, we're just going to use the same equation. All right, so you have the delta L, and that's equal to, I'm just going to use a lowercase l. So you have the delta L, which is the initial is at 10, and then times alpha, and then times the temperature difference. The temperature difference is now, the final is at 0 degrees, initial is at 20 degrees. Okay, so you can see that you have the 10, and then times 1.875 times 10 to the negative 5th, and then times negative 20. So your delta L, you will get negative 0.00375 centimeters. Okay, so this is the change in length when the temperature changed from 20 to 0 degrees. So again, you can see that it is negative, and then you're going to find the L prime when it's at 0 degrees. So L prime at 0 degrees, that will be original, and then plus your delta L. So in that case, that will be 10 minus 0.00375. You will get the value that is 9.99625 centimeters. Okay, so this is the final length when the temperature drops down to 0 degrees. And then the next one you also find is that at what temperature that the length becomes 10.009. So you can see that the change in the length. So we're going to use these equations. Okay. Now the change in length will be the final length minus initial. So the final is 10.009. Initial is at 10. So when you find the difference, that gives you 0.009. So on the left-hand side, the delta L is 0.009. On the right-hand side, you still have your 10. You still have your alpha. But then the temperature now will be the final temperature, which we don't know, minus initial temperature 20. So based off this, you'll find that you will have, after you work out the calculation and all that stuff, you'll get the 48. That's equal to T minus 20, indicating that the temperature is at 68 degrees Celsius. Okay. So in other words, when the temperature raised to 68 degrees Celsius, the change in length will be 0.009 centimeters. Okay. All right. So the third problem that I want to do is problem 27. Okay, so I'm just going to erase this. All right, 27. So calculate the minimum amount of energy in joules required to completely melt 130 grams of silver initially at 15 degrees Celsius. So you have the mass of the silver is 130 grams, and it is at initial temperature. So TI is initial temperature, that is at 15 degrees Celsius. So silver, when it's at 15 degrees Celsius, it is in solid form, and you want to find what is the minimum energy that is required in order for it to melt. Okay, so you can see that it's going from the solid and then to liquid. So there is a phase change. So if I were to do this problem, this is how we would draw the diagram like this. So you will have the silver, okay, which is in solid state, and the initial temperature is 15 degrees. Now 15 plus 273, we know that it has in Kelvin, that will be 288. Okay. So it requires energy to go from solid and then to solid again and then to the melting point. Now, what is a melting point? The melting point, if you check out the book, it's going to give you the melting point, either table 1.3 or table 1.4 from the OpenStack volume 2. So the melting point is 961 degrees Celsius. So when you add 273, that gives you 1,235 Kelvin. Okay, so this is still in solid, and then once you reach that melting point, it requires additional energy to turn solid into the liquid. Okay, so this is the liquid. So for liquid, it is maintaining at the same temperature, 1,235 Kelvin. Still maintain the same temperature. During this phase, the energy requires goes into the phase change. So you will have the normal Q, which is MC delta T, and then you have the heat of fusion. Okay, so that's a Q1 and Q2. So the equation you should be using is Q. What is the total amount of energy that is required? Will be the summation of Q1 and plus Q2. So Q1 takes care of the energy that is required to raise the temperature from 288 Kelvin to 1,235 Kelvin, and then Q2 is the energy required to melt the solid, to melt the silver from solid form to liquids. Okay, so in order to do this, there are several constants that you need to know, and we already mentioned that the melting point of silver, which can be found from the book, is this value. Okay, and then during this, you need a heat of fusion. So what is the value heat of fusion, which we call LF, heat of fusion for silver, which is 88.3 kilojoules per kilograms. Okay, so now we are ready to apply this equation to calculate the amount of energy required for this to melt. So the first one to deal with the change in temperature. So you have the mass of the silver, specific heat of silver, and then times the change in temperature, and then plus the heat of fusion. The heat of fusion will be mass of the silver, and then times the LF. And I use the plus sign because going from solid to liquid requires a lot more energy. So you need to use plus. So before we plug into this equation with the values, we also need the specific heat of silver. So the specific heat of silver, if you check out the book, from table 1.3, you'll get this value, 336 joules per kilograms per Kelvin. So when you do this, everything has to be in SI unit. The mass is 130 grams, which means that it is 0.13 kilogram, and then times the specific heat, which is 236, and then times the change in temperature. The change in temperature, the final temperature is this. Initial temperature is 288. Okay, so this is the amount of energy to raise the temperature, and then plus the mass times the specific heat, times the the heat of fusion, which is 88.3 kilojoules per kilogram. So you need to multiply that by 88.3 and then times 1,000, because everything is in SI units, so it should be in joules, not in kilojoules. So when you plug in this equation and then punch into the calculator, you will get the value that is, the first term will give you 29023.28 joules, and then plus the second will give you the value that's 11479. So when you adding all this together, you will get 40,502.28 joules. Now, if you want to change it to a scientific notation, you can get 4.05 and then times 10 to the fourth joules. Okay. So this is the problem that tells you, when you have the energy that goes not just to change the temperature, but also change the phase if there's enough energy to do so. Okay. Alrighty.